So we're in Unit 6. We're talking about conservation laws, and we've been specifically looking at collisions and the law of conservation of momentum. So we're looking at elastic versus inelastic collisions right now. Phil physics student is alone on a frictionless ice pond. He has no one to push him. Also no one for him to push. The Super Bowl is about to start, so we want to rescue him in the quickest way possible. So we take a basketball out to the pond and throw it to him. Should he catch it, or should he let it bounce off his chest? Which one will get him off the ice faster? So we have some numbers. The mass of the student is 100 kilograms. The mass of the ball, 2 kilograms. The initial speed of the ball, 10 meters per second. So, an inelastic versus an elastic collision. An inelastic collision is where you would catch the ball. So remember, inelastic, we have hit and stick. This is basically the catching situation. So I'm going to draw some pictures before. So we have a ball. Its velocity is 10 meters per second. And here is the student on the pond. And the student is not moving. Velocity is 0. After this inelastic collision, here's the ball, here's the student, and there is some sort of a velocity, and it's x. So this conservation law says the mass of the student times the velocity of the student, this is the initial, plus the mass of the ball times the velocity of the ball, that's the initial, equals the mass of the student times the new velocity of the student, and the mass of the ball times the new velocity of the ball. So plug in some numbers. The mass of the student is 100 kilograms, but his velocity is 0. And we have the mass of the ball, which is 2 kilograms, and its velocity, which is 10 meters per second, equals, here we have the mass of the student times new student velocity and mass of the ball times the new velocity of the ball, x. So running the numbers, this is 0 plus, here we have 20 equals, all of this is 102 times x. Divide both sides by 102, and we find that x equals 0.196. And if we were keeping track of the units, it would have been let me just make some room for this. Kilograms canceled, you're left with meters per second, which is a velocity, which is what we're looking for, the new velocity, which is x. And so we call this velocity prime 0.196 meters per second. Now let's look at this from the terms of an elastic collision. And so, draw my pictures. Here's the before. Here's the ball coming in at 10 meters per second. Here's the student. Here's the after. The student let it hit him in the chest. He now has a velocity of x in the original direction of the ball. And the ball, it tells us, bounces back at 5 meters per second. We want to be careful here. These are opposite in direction, so they need to be opposite in sign. So, like a number line, if I draw something going right, I usually make it positive, and going left, I usually make it negative. So, using our same law, make some space here. The mass of the student times the velocity of the student. The mass of the ball times the velocity of the ball. Both of these are initial conditions. And here are the new conditions. We have before and we have after. So plugging in numbers, the student is still 100 kilograms, velocity is 0. Plus the mass of the ball, 2 kilograms, and its velocity was originally 10 meters per second. Over here we have mass of the student. Student's velocity is now x, positive x. Mass of the ball, and the velocity of the ball is now 5 in the opposite direction, which we'll call negative 5. So simplifying all of this, we have 20 equals 100x, and that's minus 10. So add this over. Now we have 30 equals 100x. We find that x equals 0.30. So we're going to say the new velocity of the student is 0.30 meters per second. And if you were going to put in the direction, it would be in the original direction of the ball. So let's compare these two. At the inelastic collision, the student moves off at 0.196 meters per second. And in the second one, where he lets the ball hit him and bounce, he moves off at 0.3 meters per second. Is this surprising? What happened? If he catches the ball, he's going to gain momentum. If he lets the ball hit him, he's going to gain momentum. But here's really what happens. So if you catch the ball, you gain some momentum. And then when you throw the ball, you gain more momentum. Basically, in the elastic collision, the student did both. The ball hit him, which is the same as catching it, and then it bounced off of him. This would be the same as if they threw it. So he did both. Did the result of the preceding experiment surprise you? Analyze it this way. If Bill had the ball in his possession to begin with, he could have just thrown the ball to be propelled in the opposite direction. In the inelastic collision, he just caught the ball. In the elastic collision, he caught the ball and threw it in the opposite direction, both actions helping to propel him off the ice. So maybe we can put in a circumstance where, even better, catch it and throw it back at greater than 5 meters per second. Now we're going to look at two-dimensional collisions. So far, all of our collisions have been one-dimensional, meaning on a linear track. To handle the vector nature of momentum, all we had to do was make sure we watched the signs of our velocities. But we said that momentum is conserved if the collision occurs at any angle, or meaning in two dimensions. Now to handle the vector nature of momentum, we have to return to the I's and the J's. We will work through an example of a two-dimensional collision to see if momentum is conserved. So sketch of a collision between a solid ball and a striped ball as seen from above. So we're going to draw basically like this. So we're going to have a striped ball. There it is. And a solid ball here. And they are going to come together and collide right here at the origin of this. So let's try this again. Here's the original velocity of this ball. And we have this ball. And we're using this data down below. So the striped ball has a mass of 320 grams. Its initial velocity is 40 meters per second. And its angle with the x-axis here is 20 degrees. Okay. Afterwards, it has a velocity of 20.5 centimeters a second, and its angle is going to be 60 degrees. So it's going to look something more like this is 60. Here's the ball, and it's moving off in this direction a little slower. So these two go together, and these two go together. We've looked at this one, we looked at this one. Now for the solid ball, which originally has an angle of 40 degrees from the x-axis. And then afterwards, it's going to move off in this direction, an angle of 50 degrees from the x-axis. Draw this a little bit shorter. It lost some speed in the collision. There we go. So we're just going to keep the units we have, grams, centimeters, not a big deal. We're not going to end up with newtons, but everything here has the same unit and it's going to work out the same. So for now, we're just going to stick with the units we have. So a sample calculation, one of 4 of these, the striped ball before the collision. So here's what happens. Here's the striped ball. It is moving like this. Make that a little longer. And we need to find the I component and the J component. So we want to know the horizontal component. That's I. And we want to know the vertical component, which is the J. That's going to form a right angle, horizontal versus the vertical. So when we look at this, we have this one as 20 degrees because it actually hit. This was 20. We want to know, do we know any of these sides? So do we know the original here? We're talking about momentum. We're not talking about velocity necessarily. So this is not 40. This is going to be P. P is momentum, 320 grams, which is mass, times 40.0 centimeters per second, which is its velocity. So we find that this has 12,800 grams times centimeters per second of momentum. And that's this, 12,800. So to find the horizontal and the vertical, so to find J, we know the hypotenuse and we know the opposite angle. Sine of 20 degrees is the opposite, J, over the hypotenuse, 12,800. And so your minimum step, J equals 12,800 sine of 20 degrees. And so J equals 4,380. To find I, we have the adjacent side to the angle and the hypotenuse. So we're looking at cosine of 20 degrees is I over the hypotenuse. I equals 12,800 times the cosine of 20 degrees. And I equals 12,000. So that's the striped ball. And if you look here, just a little bit below, we have a place for this data to go. So we found the momentum to be horizontally 12,000, and it's moving left to right. We're going to call that positive. And then its vertical component, it is moving from the top of the page towards the bottom of the page. So we're going to call that negative 4,380. So these calculations won't necessarily give you the sign. It will give you the number, and we have to figure out the sign for our own. This is why the picture is extra important. So let's go ahead and do another sample calculation, and I'm going to get rid of some of this. And let's look at the solid ball. The solid ball beforehand. So here's the solid ball. We can find its momentum. It has a mass of 420. It has a velocity of 30.0. (12,600) grams times centimeters per second. This is the momentum. Here it is. And we want to know its horizontal component and its vertical component. So I'm going to take the shorter method here. I equals cosine, just put that number, angle is 40. I equals cosine, I equals 12,600 times the cosine of 40 degrees. And so it is 9,650 for the number. We have to figure out the direction. Now for the striped ball, we said that going left to right was positive. This one is moving right to left, and so it has to have an opposite sign. Negative 9,650. Then for the vertical, J equals 12,600 times the sine of 40 degrees, which is 12,440, and it is, looking at the wrong spot on my paper. It is 8,100, and it is moving from the top of the page to the bottom. That's going to be negative. And so we can put these numbers here. Negative 9,650 and negative 8,100. And so we can figure out the total momentum of the system before the collision. So add these two together, 2,350. Add these two, negative 12,480. So after the collision, I'm going to erase this. Do the next part. After the collision, let's look at the striped ball. So look at your picture here, and here's the striped ball. It is now moving this direction, and its momentum (320 grams). Now its velocity is 20.5, and its momentum, grab a calculator here, 6,560. So we need to know horizontal component, vertical component. So I equals, let's put in the angle here. I equals 6,560 times the cosine of 60. And we come up with 3,280 for the number. And now let's figure out positive or negative. We're moving right to left in our picture that's been negative so far. And the vertical, we're going to use the sign. And we end up with 5,650. It's moving on our page top to bottom, which has been negative. And let's go ahead and fill in our numbers here. With the striped ball after. And one more time for the solid ball. Here's the solid ball. It's momentum. We want to know horizontal. We want to know vertical. And this angle is 50. So some numbers here. 5,670. This one, 6,760. And figure out the directions. Horizontally, we're going left to right, positive. Vertically, we're going top to bottom, negative. Same thing as the before situation. We are going to add the I's and the J's for the after. The total momentum after 2390, negative 12,440. And they're not exact, but numbers are close. We can probably say is the result of rounding. The total X momentum before 2,350, and the units are grams times centimeters per second. Afterwards, 2,390 with units. In the Y direction, 12,480 and 12,440. And we're going to look at percent difference here for a minute. And so percent difference equals, we're going to say 2390 minus 2350 over the average is 2370. And we're looking at some numbers in the X direction, 1.69%. And in the Y direction,